In this video for section 6.5, I'm going to show an example of finding the arc length of a curve when we are integrating with respect to y. And this is actually an example that's done in your book, example 6 on page 449. And typically I wouldn't redo an example that's already done in the book, but I feel like there's so much in here, algebra-wise, that's tricky and not obvious, that the book kind of goes from step to step, assuming that it is, and it's really not. So I want to take the time to explain what's going on and show each step. So we're starting off with this example of a natural log function, and we're given an interval from a to b, and it actually tells us that we want to integrate with respect to y in order to find the arc length here. So one of the first things that I have to do is write a function g of y, or in other words, take the given function and solve it for x, write it in terms of y. So again, starting right off the bat, I feel like the algebra is not necessarily obvious here. If it's been a while since you've taken algebra, you may have forgotten how to find the inverse, essentially, of a natural log function. And so what we do is we use the change of base formula, or actually that's not the term that is used here. What I mean to say is that we're going to use the base and raise it to the power of y, and it's going to equal the argument. So that's just the basic rule for how to convert a log function into an exponential function, which is always the inverse. So the base of a natural log is e, and then again I'm going to raise it to the power of y, and it's going to equal the argument x plus the square root of x squared minus 1. So what I want to do in this equation is isolate the x variable, but you can see that I have two separate x terms that can't be combined, and so what I need to do is get rid of this square root. So to undo a square root, I need to isolate that term and then square both sides. So let's do that. So we isolate the square term and then square both sides of the equation. On the left side here, I have a binomial that's being squared, so I have to use the FOIL method. E to the y times e to the y is e to the y squared, which is the same as e to the 2y. So remember your power rules and your exponential rules. Here I'll have x times e to the y, and then another negative x times e to the y. So that'll be negative 2x times e to the y. And then lastly, I'll have a positive x squared. Squaring the right side is much easier because the square and the square root cancel each other out, which was the goal in the first place. Alright, now we want to gather our like x terms and isolate the x. What's nice is that we have x squareds on both sides of the equation that cancel each other out. So we're really only left with one term that has an x in it, and that's perfect because again, that's what we're trying to solve for. So let's isolate this term. I'll subtract e to the 2y from both sides, and then let's divide in order to get x alone. Okay, so I have now isolated my x, or in other words, written a function in terms of y rather than in terms of x, which is how it was initially given. Okay, so I just rewrote it down here as a function of y, g of y, as opposed to x. Now the other thing that we're going to need to do is we're going to need to change the interval. So we rewrote the function itself in terms of y. Let's rewrite the interval in terms of y. So the given interval was 1 comma square root 2. So what we want to do is we want to take 1 being an x value and change it into the corresponding y value according to the rule or the function that's given. So I'm going to take 1 and I'm going to plug it into the given function. and I'm going to find its corresponding y value. I'm going to do the same thing with the square root of 2. I'm going to plug that into the given function, and I'm going to simplify each one so that I get an actual value. So let's look up here. 1 squared is 1, 1 minus 1 is 0, and the square root of 0 is 0. So what I get here is that y is going to be the natural log of 1, and hopefully you remember that that always equals 0. So in terms of my limits of integration, my new lower limit is now 0. Let's simplify this expression. The square root of 2 squared is 2. 2 minus 1 is 1. The square root of 1 is just 1. So what I end up with is the natural log of the square root of 2 plus 1. And again, that is my new upper limit of integration, which you can see I had to squeeze in there because I didn't leave enough room. But we have everything in terms of y now. We have a function in terms of y. We have an interval in terms of y. We're ready to start looking at the arc length formula. So remember that arc length is found by integrating over the interval, which is now in terms of y, 0, natural log, square root of 2, plus 1. Sorry, I extended my square root of 2 a little longer than it needed to be. The plus 1 should be on the outside. And then I need to take the square root of 1 plus my g prime of y function squared, and then integrate that with respect to y. So what I'd like to focus on now is this piece. So I need to obviously find the first derivative of the function that I wrote here, and I need to square it. Once I do that, I'll plug it back in here, add the 1, simplify, square root the whole thing. It's certainly not an easy process, but we'll get to it. Alright, so let's work on just the g prime of y part first. So let's kind of isolate that step, do it to the side, and then we'll plug it back in. Well, starting off with just our regular g of y, we wrote that as this fractional expression that has e to the y, or some form of e to the y, in the top of the fraction and in the bottom of the fraction. So what we're actually going to do is we're going to factor out a negative e to the y from the top expression, and then that's going to allow us to cancel this e to the y out of the bottom. So let's see what happens when we do that factoring. Again, I haven't taken a derivative yet. I just want to simplify my original function before I do. So I'm going to factor out a negative e to the y from the top. I need to take 1 and I need to divide out e to the y. So when you do that, you actually get e to the negative y. And we can check that really quickly. Think about multiplying these back together. When you have the same base, you would add the exponents. So this would give me negative e to the 0, because when I add y and negative y, it becomes 0. So e to the 0 is really just 1. So that does work. Let's factor it out of the second term as well. Watching my negative signs, I know that this is going to become a positive. So if we factor out an e to the y from an e to the negative 2y, sorry, I just realized that I put that negative in all on my own. It never existed in the first place. If you go back up and look right here, that was just a positive, e to the positive 2y. So let's fix that, and then go ahead and factor out an e to the y, and I'll just be left with another e to the y. You can do a quick check of that, once again, by just multiplying. If you take e to the y times e to the y, you do get e to the 2y. So that's a little bit of tricky factoring, but again, the reason that we did it was so that we could cancel that e to the y out from the denominator. In addition, I could also cancel out the negatives, so I tagged that along. But it makes it really nice now because I don't really have a difficult denominator at this point. My denominator is just a constant. So it's going to be easier once you've simplified to first of all find the derivative, and then of course square that derivative, add 1 to it in square root, and ultimately integrate. So there are lots of steps going on here, and at this point all we have is just our g to the y, g of y simplified. We haven't even taken the derivative yet, so that's my next move. Let me switch paper here. Alright, so back to our simplified g of y function. Let's take its derivative. Now the nice thing is that this 2 is really just a 1/2, which is a constant. So when I'm taking the derivative of something that has a leading constant, I can just keep that constant aside and multiply it back in after I've taken the derivative of the rest. So let's go ahead and take the derivative of the numerator here. If I take the derivative of e to the negative y, it's going to be negative e to the negative y. And if I take the derivative of e to the y, that stays the same. So there is my beautiful derivative of my g of y function. Remember, in addition to taking the derivative of it, it also needs to be squared. So let's go ahead and do that before we plug it back in. So squaring 1/2 times negative e to the negative y plus e to the y. When I square, I can square my 1/2 constant multiple, which will give me 1/4, but a little bit trickier when I'm squaring this piece because it is a binomial, so I do have to FOIL that out. So let's first of all take negative e to the negative y and square it. The negative becomes positive, and if I have e to the negative y times e to the negative y, that's e to the negative 2y. If I multiply negative e to the negative y times positive e to the y, first of all I get a negative, and then I add my exponents. Y plus negative y is 0. So I get negative e to the 0, which hopefully you guys are noticing is actually just going to be 1. Now FOILing, I did first, I did outer. If I do inner, I'm going to get that exact same thing. My two inner terms are going to be the same, my outer and inner terms, I should say. And then if I square the last piece, that'll give me e to the 2y. Cleaning this up, I've got 1/4 e to the negative 2y minus 2, because remember this is 1 and this is 1, plus e to the 2y. Alright, so the arc length can be found by integrating from 0 to the natural log of the square root of 2 plus 1 of the square root of 1 plus all of this with respect to y. So the next step is going to be for us to get a common denominator and combine all of this, and then we're actually going to factor it, simplify it, and square root it before we ever integrate. Unfortunately, I'm out of time on this particular video, so I'll have to stop here and then come back in a second video to finish this up.